Now that we've learned all the different ways to make amines, the next thing that we want to learn is the reactions that amines can do. The first reaction that we're going to learn is called the Hofmann elimination. Hofmann, same guy that we learned about when we were doing Zaitsev, Hofmann, that type of stuff. This is an elimination reaction, just like you did in fall quarter. So that means because it's an elimination reaction, we are going to be converting our amines to alkenes. Amines can be converted to alkenes via E2 elimination. And even though you've already learned about the E2 reaction, this is actually quite a bit different than what we did with elimination in the fall quarter. Overall, the general overall reaction is going to be our amine, and in an E2, we're just going to kind of put that in parentheses underneath, end up with an alkene. The reaction in general is similar to dehydration of an alcohol, just in terms of the challenges that we have. The reaction is similar to alcohol dehydration. So in the alcohol dehydration reaction, you're going to use the same size carbon chain. And this is an acid catalyzed reaction, the conversion from an alcohol to an alkene. So we'll ultimately end up with the same product. In both cases, whether we're looking at the amine reaction elimination or when we're looking at the dehydration of an alcohol, in both of those cases, the leaving group is terrible. In both cases, we have a bad leaving group, and that's really the biggest challenge with these two reactions. We have, in the dehydration reaction, we have OH, and it's a bad leaving group because it's a really strong base, and strong bases are bad leaving groups because they're reactive when they come off the molecule. So we get rid of the OH minus, and it's not content to just sit there and be gone from the molecule. It wants to do some sort of reaction. And then in the case of the amine, the leaving group would be NH2, which is an even stronger base than hydroxide. So it's the same problem, but even more significant. We solved the alcohol dehydration problem by protonating, just protonating the alcohol. So in the alcohol dehydration, before we can do the reaction, we are going to protonate the OH group, which converts it to water, which is a good leaving group. And this is a really effective strategy. So just as a reminder of what that looks like, I'm just going to use H plus as our abbreviation for the acid. And all that we're doing here is just converting that OH group to what will be a water molecule when it falls off of the molecule. So now it's in good shape and ready to do elimination reaction. With the amine, we can't quite do the exact same thing. For the amine, the Hofmann elimination, instead of protonating it, we are going to alkylate it. And this is going to convert it to a good leaving group. And we learned how to alkylate amines last week. And so we're just going to use the same type of strategy in this process. And I'm going to actually make my carbon chain a little bit more interesting because it's going to become relevant in the next step. So I'm just adding another carbon to the chain. For the alkylation, we want to completely and totally alkylate that nitrogen. So that means that we want to use excess of our alkyl. And the ideal alkyl halide to use for this is methyl iodide. And I'll explain why. For now, for starters, we are not really trying to, our goal is to just get rid of the nitrogen completely. So when we're loading the nitrogen up with our groups, we don't really care that much about what they are. They're just going to end up in our waste container. So we want to put the smallest possible alkyl groups on the nitrogen to minimize the steric hindrance that we're going to encounter in the reaction. So that's the reason that why we're choosing methyl, and we will talk about why we choose methyl iodide specifically, because I know that normally when we're picking a halogen, we just default to bromide, so it's interesting that we're using something different. So here's the product that we're going to get, the totally alkylated nitrogen. And once we get it to this step, we're almost ready to do the elimination. The ammonium, this is an ammonium iodide that we made. The ammonium iodide, which is this stuff right here, is not a good candidate for elimination for E2. Is not a good E2 reagent. I feel like really compelled to review E2 briefly with you because it's been so long since we did E2. E2 stands for elimination, second order, which means that you have two molecules colliding in the first step or the slow step of the reaction. So in the E2 reaction, we need to have a reactive and strong base, so that reactive strong base is going to just attack our molecule, attack one of its protons, and initiate the E2 process. So we need a base that is reactive and strong. And this guy, iodide, he does not meet the criteria for that. The iodide is stable, and it's not even a base. So it's not going to do the E2 reaction unless we mess with it a little bit. So for the next step, the next thing that we are going to do is convert our ammonium iodide to an ammonium hydroxide. And that's a very simple conversion. So I'm going to bring back our alkylated ammonia with the iodide ion. And all that we are going to do with this is add silver oxide, and this is going to be with water. And this does not have any effect on the ammonium part of this compound, so we still have the exact same organic. It converts the anion from iodide to hydroxide because the silver iodide, AgI, is an insoluble precipitate. So that silver cation from AgO is going to precipitate out the iodide ion, and that initiates another reaction that generates hydroxide ion. And as you know, hydroxide is a great base. So this is a great E2 reagent. And now we are totally ready to go. Once we have formed that hydroxide, it is going to begin the elimination reaction. It's still a little bit of an uphill battle, so this part of the reaction is usually heated. Heat is going to be necessary to get it to go. And because of the steric hindrance of this guy right here, so this is very bulky, we are going to be forming the least substituted alkene. hence the whole Hofmann thing. The hydroxide is going to go after a hydrogen on a carbon that is on the outside or end of the molecule because it is more accessible. This is E2, which means all these things are happening at the same time. We're not forming any kind of carbocation or anything like that. And we end up with the least substituted alkene. We have this tertiary amine byproduct and some water that's being formed as well. The major product of this reaction is the least substituted alkene, and this is due to the sterics of the leaving group. But we will see minor product of the more substituted alkene. So in our reaction, it would be this guy. And then also always never forget cis and trans.